So welcome to lecture 16. So we'll continue our discussion on list decoding of codes. So last time we have seen the combinatorics of list decoding codes. We have introduced the notion of list decodable code, which is the ability to be able to decode beyond the unique decoding radius, beyond distance by 2. We showed that this can't be more than 1 minus h of rho. If it can't be more than 1 minus rate. 1 minus rate. Basically, the list decoding radius can't be. At that point, the number of code words becomes exponentially large. So it could be anything. Well, then we showed that for every code, it's at least the Johnson radius. Up to the Johnson radius, the list sizes are polynomial. But all of these were combinatorial results. They just showed they were results of 2 flavors. They showed that there exists a code which is list decodable all the way up to 1 minus rate. This was a probabilistic construction, and said that every code is list decodable up to the Johnson radius, with both combinatorial. What we will now be focusing is trying to get codes in which the corresponding list decoding things have efficient algorithmic implementations. In particular, we'll ask if several of the codes which we have studied so far, more precisely, Reed-Solomon code, which something we want to like. This one, does it have a list decoding algorithm, and how efficient is the list decoding algorithm? What is the list decoding radius of the Reed-Solomon code? Up to what point can you algorithmically list decode? So we know up to the Johnson radius you can, and we'll ask, can up to the Johnson, at the very least up to the Johnson radius, can you algorithmically list decode the Reed-Solomon code? The Reed-Solomon code might also be list decodable beyond the Johnson radius. That I don't yet know. It's actually still an open question. The Reed-Solomon code is decodable, but we do certainly know combinatorially it's list decodable up to the Johnson radius. And the focus of today's lecture will be trying to come up with an algorithm to see if Reed-Solomon is also algorithmically list decodable all the way up to the Johnson radius. Okay. So, we're going to look at list decoding. In particular, we're going to look at efficient list decoding of the Reed-Solomon. Probably in the next lecture. So let's state our problem. Let's state exactly what the question is. So what's the problem? The problem is the following. You're given an input. Just describe what's the input, what's the desired. One, the input is, so there's of course a finite field F. You are given n, which is the number of evaluations. You were given k, which is the degree parameter. Rather, we'll assume that the degree is always, so that k matches with the notion of dimension, degree is always less than k. It's not equal to k, it's less than k, therefore, that will exactly be the dimension of the code. Then, t, this is something which we haven't put so far, is what we call the agreement parameter, the number of points of agreement. Parameter. Sometimes it's equivalent denoted by n minus t, which is the number of errors. Then you are given alpha 1, alpha 2, alpha n distinct points. These are the evaluation points in S. You're given these n distinct points. Now, in addition to this, now you are given that's just a specification of the Reed-Solomon code. Now I have to give a purported received word. So what's a received word? It is some R1, R2, Rn at these n locations. So just to match with the beta, the alphas, I'm going to call it beta 1, beta 2. So beta 1, beta n are n field. not necessarily distinct. So that's the input. And what's the output that we want of this one? Find all polynomials px in fx of degree less than k, such that these polynomial, when you look at it at the evaluation point, it agrees with the beta on at least t points. That is the number of I in 1 to n, such that p alpha I equals beta I is greater than that's okay. And question is find efficient algorithms for above problem. With as low t as possible. So you want the number of agreements, even if the number of agreements are very, very small, you still want to be able to. That's the so that's if you're comfortable with that's the problem if we want to solve. And we want to come up with algorithms which do this for there are various parameters floating for us, n, k, and p. So think of n and k as fixed, they describe the code. And now for a fixed n and k is a parameter, you want to come up with an algorithm that achieves it for the smallest possible t, where t is in terms of n. So let's just remind ourselves of a few things. So in observation, so t greater than n plus k by 2. This is exactly the unique decoding radius. I'm writing it in terms of agreement. So far, we have been writing it in terms of errors. So it will be errors is less than n minus k by 2. Now I'm going to write everything in terms of agreement. It's a cleaner parameter to work with in the setting. So we want to going from unique decoding to list decoding, we want to allow more errors. That means the agreement is going to keep falling down. Okay. So this is exactly the unique decoding radius. And we know that the Welsh-Berlekamp algorithm achieves it up to this point. There are various other algorithms also, but Welsh-Berlekamp certainly gets it all the way up to this. Now, what is the Johnson radius? The Johnson radius we saw was up to 1 minus square root 1 minus delta. So that's the fractional distance of the up to which you can recover. In other words, the agreement is square root 1 minus delta. So p being greater than square root nk, this is the Johnson radius. That's the Johnson radius. So you want to be able to recover even from p as small as square root nk, which is significantly small. And the reason I'm writing this is smaller than the unique decoding radius. It's a geometric mean of nk, which is smaller than the arithmetic mean. The unique decoding radius says you can go all the way up to n plus k by 2. Johnson radius says you can go all the way up to square root nk. And that's only a combinatorial. So this is just combinatorially. What we are asking is, can we achieve this algorithm?
So we are just looking at alphabet independent.
We are looking at alphabet independent Q because Reed-Solomon setting is when Q is larger than n. So the alphabet dependent Johnson bound doesn't give anything better than the the alphabet independently. And what we'll see today is a sort of an algorithm scheme due to Madhusudan from 96, which first gets t greater than square root 2kn. And then it was further improved 2 years later by Venkat, Guruswami and Sudan. 98, it went all the way to this rate. Okay. There will be some fudge factors here. It will be not exactly, it will be the 1 plus epsilon times square root n and this one the actual algorithm. But if you write it in terms of rate, it will be exactly this is going. So in terms of rate, this will be that the delta will be with the delta. This is as long as delta is less than 1 minus square root r. This is this is going to be delta less than 1 minus 2 square root r. Sorry, not delta, we will be calling it rho. And this will be rho less than 1 minus square root. So the goal for today's thing is actually to look at Sudan's algorithm and the subsequent improvement due to Guruswami-Sudan. So for this, the starting point for both these algorithms is the Welch-Berlekamp algorithm. So let's take the Welch-Berlekamp algorithm, stare at it for a while and see what changes can we make to it so that now it can become a list decoding algorithm. So let's just recall the Welch-Berlekamp algorithm. So how did that algorithm go? So it had two significant steps. Step 1 is find all non-zero pairs of polynomials NE such that the following happens. I'm just recalling the Welch-Berlekamp algorithm which we did in class. Firstly, degree of n was less than or equal to t plus k minus 1. Degree of e was less than or equal to t, and n of alpha I was equal to beta I times e of alpha I for all I in 1, 2. So basically, this was the key equation for us. We came up with an explanation of all the points. So for every pair of points, the points are alpha I, beta I, we came up with an explanation for them. So we came up with a polynomial n and a polynomial e was not too large a degree, n was not too large a degree. These were non-zero polynomials. Why do such polynomials exist? It will be just stated by the fact that the number of variables is less than the number of equations, more than the number of equations, so there will be a non-zero solution. That's exactly what we did. So step 1 was this, and step 2. Step 2, we just saw that you output n by e. This miraculously we gave an analysis that this will find if there is a polynomial p that agrees with the list beta I and more than n plus k by 2 points, we observed that this polynomial will actually be this ratio. It doesn't matter which non-zero solution you lay your hands on, every non-zero solution will give you this. In other words, every non-zero solution. So let's stare at this a little more. So let's stare. So it takes if you look at this polynomial q of xy, which I define to be n of x minus y times p of x. You stare at this polynomial, what are we stating? We are stating that every p, any p that is a valid solution to it, is the root of this form. Qx comma p of x is identical. With every p, in fact, there is only one p that has agreement greater than n plus k by 2 satisfies. This is just a more sophisticated way of writing. This is just a more sophisticated way of writing that p of x is the ratio n of x by u of x. When I plug in the bivariate polynomial q of xy, the polynomial p of x, this is bivariate. When I plug this in, this thing identically vanishes. So this was the Welsh-Burleigh answer. So just stare at it. We did this in detail. This was our, what we want to do is we want to sort of endo this further so that now we can go beyond the unique decoding radius. Notice in this case, there won't be a unique p, there will be several p's that we will need to do. But the broad outline will be the same. So we'll find the first step will be find a algebraic explanation for all the n points. And then the second step, show that every polynomial p that significantly agrees with the data on more than say t points, we would like to make t as small as possible, can be extracted from this algebraic explanation. An alternate way of stating this, notice that this is the same as stating that is y minus p of x is a factor of q of x. These two are the same statement. So why am I doing all of this? Because now I want to get more than one p. I want to firstly get more than one p of x. We are going to enter the list decoding regime. So what we will try to do is, we will also do the same thing. We will find out some explanation from algebraic explanation for the points of the first step. Previously it was n and e, which was exactly we were basically finding a bivariate polynomial q of xy, so that the degree in y was 1 and the degree in x was something like that. Which had some restriction. We found some bivariate polynomial in x and y that explained the data with some degree restrictions. And the degree was chosen such that the number of monomials was slightly larger than the number of equations, number of evaluation points n. Therefore, they always exist as a non-zero bivariate polynomial that satisfies this. And then once we have the bivariate polynomial, we extracted the polynomial p of x by just stating it's a factor of this bivariate polynomial, y minus p of x. And that's going to be our broad approach. We are going to the student's extension. Generalization. It's going to be on similar lines. Step 1. Find an algebraic means explanation for the data points. In the form of a bivariate. Bivariate polynomial q of xy. Step 2. Output all factors y minus p of x of t of x. You also have to check that this there might be spurious factors, but once you have a factor output of What I mean this, I just mean output all polynomials p such that y minus p of x is a factor of q of x, y. But some there might be some factors which are spurious factors. But given a polynomial p, you can check if its agreement with the data is more than p or not. You can explicitly do this check. So this is what we sort of do the generalization of one. And the key idea is going to be now, previously we could not expect to get more than one polynomial because the degree in y was 1. So his first step is going to be, I will do the same thing. I'll give a bivariate explanation in which the first step you allow for super degrees in y which are more than 1, slightly larger than 1. So hoping that all the polynomials that have non-trivial agreement, significant agreement with the data will all appear as factors. Right now, there's only one factor, y minus p of x. I want, suppose there are L polynomials, P1, P2, PL. I want y minus P1 of x, y minus P2 of x, all the way up to y minus PL of x, all of them to be factors of Q of x. There's no reason why this approach should work or something. We are taking Berlekamp Welsh, we're playing around with it, and that's what's exactly going to do. We're going to do it, and students algorithm miraculously what we'll play around with these things. What can we do and stuff? We will see that actually it will improve over the unique decoding radius up to a particular point. And then later on, we'll see if we add one more additional, this one due to Guruswami-Sudan later on, it actually goes all the way up to the Johnson. Question from this. So there will be a couple of things. We must ask, why are these two steps? So in Berlekamp Welsh, it's very clear that these two steps are efficient. The first step is just solving a linear system. So that's an efficient one. It's a linear system. Second one is just division. So that's also easy. So now if we should ask the same thing over here, if we're going to try this general approach, this will also once again almost always be solving a linear system. So this will be similar. This one, now you should ask, I want to lay my hands on factors of the form y minus p of x. Surprisingly, factorization over polynomials, over finite fields happens to be a polynomial time algorithm. So we will keenly use this fact. This is a non-trivial algorithm, but we'll just use it as a black box. Step 2 requires efficient factorization algorithms for bivariate polynomials over finite fields. And assume this as such algorithms exist. Fantastic results in this. We will Cartograph gave such algorithms and Berlekamp also. We'll take these on faith for now.
These are random.
These are randomized algorithms. These are randomized. So it depends. They are randomized if you wanted to run in log of the field size. If you're allowing to run, so they are deterministic algorithm if it's allowed to run polynomial time, log of the characters. If you are allowed to run in so for example, for GF2 fields, you can get determinant. So let me tell you, what's the state of algorithms? There are algorithms which run in polynomial time in the characteristic and the data. And there are randomized algorithms which run in polynomial time and the log of the field size and the data. Therefore, in particular, if the field is a GF2 field, then the first algorithm gives you a deterministic algorithm. There are sure algorithm. If the field is not a GF2 field, it's a large prime field. The first algorithm runs in polynomial time in the characteristic, which is not, that's polytime. It's not a very impressive algorithm. What we would want is actually polynomial in log p. So for our purposes, poly in n is okay. So for this purposes, sometimes we would want it to be super efficient. We don't have such algorithms. So these are randomized algorithms, but for the purpose of this, we can assume they actually are deterministic algorithms. They exist algorithms run poly in the field size. So the randomization helps if you want the algorithm to run a poly in log of the field size. We don't, in this context, we will not be distinguishing between those. So this will make a sense only if the field is very, very large compared to n, but already the field is like exponentially large compared to the n. You could still ask this problem, the Reed-Solomon question. And in that case, these algorithms won't be efficient. But we are going to talk about fields which are just slightly larger than n. I don't know if all the discussion which I said the last 2 minutes made any sense. So the distinction between randomized factoring algorithm and deterministic factoring algorithms comes in what's the dependence on the field size, whether it's log of the field size or poly in the field size. Here all our algorithms are allowed to be poly in the field size because the field we think of it as something that's polynomial in n. Therefore, it doesn't matter. We do have deterministic algorithm. If you want to go for the setting in which the field is really, really large, then you don't. Then you have to go only to randomized algorithms. And by the way, that's an interesting open question, whether those randomized algorithms can be de-randomized. So let's do students. In fact, let's do a first attempt for student. Our key thing is now, the only thing is we are now going to go from, we had this bivariate polynomial q of x, which was the form n of x minus y times e of x. It was a bivariate polynomial degree 1 in y. We are going to allow larger degrees and then see how this is going to help us. Okay, so that's basically going to be one. So this will be parameterized, there will be a parameter L, which will tell you really would like this parameter. This is the y degree, but then it's actually going to be the x degree. So what we're going to do, step 1 is going to be the following. So, and this is the parameters are of course the parameters. Parameters are always n greater than k greater than 1. That's always the parameter given to us. Then there is p, which is the agreement parameter. And then there's going to be one other parameter which is going to control the. So right now so far we had y degree to be 1 in the Welch-Berlekamp setting. We are going to allow for y degrees to be larger than 1, and L is going to control them. L is going to be that one. So let's given that we'll eventually set L to be a particular choice, which will give us the proven problem. So step 1 will be find a non-zero polynomial. Non-zero polynomial q of xy such that now I need to put restrictions on what this one is. So we say that one, the degree in x of q is at most L. The degree y in q is at most n by L. It will be clear why we choose these parameters L and n by L. And then later on we'll see further improvements there. And Q of alpha I comma beta I is 0 for all only. So that is sort of the algebraic explanation of the data points. Notice the only reason, so what actually, let's quickly see why am I doing this choice of L. How many Qs are there? How many, what? So basically you want to show that such a non-zero Q can be obtained. In other words, this is a system of equations. It's an equation in the coefficients of the bivariate polynomial Q. You're going to write the system of equations and solve it. And for that, you need the number of variables should be larger than the number of equations. What's the number of variables? It's exactly the number of monomials such that the degree of x is at most L and the degree of y is at most n by L. What's that?
N plus N plus N plus.
It's L plus 1 into n. Yeah. It's exactly L plus 1 into n by L plus 1. This is a number larger than n. That's all I have. The reason for choosing n and n by L is exactly to ensure that the number of monomials that any such Q will have is larger than n. Therefore, the number of equations, these equations, is a number which is smaller than the number of variables. Therefore, there will be a non-zero solution. That the L and n by L have been just chosen for that reason. Step 2. Find all polynomials P of x in f of x such that y minus p of x is a factor of q of x, fine. So here you will assume because we have factorization routine, we'll just factorize q of xy, stare at all its factors. Notice every y minus p of x has to be an irreducible factor. It cannot be factorized further. So look at all these y minus p of x, find all such polynomials and output, find all them and output list of all such polynomials, all such p, such that two things happen. One is the degree of p. The degree, there's only one p is strictly less than k. It should be one of it could have had a factor which is more larger than k. I'm going to ignore those factors. And furthermore, the number of I in n such that p alpha I equals beta I. This should be larger than or equal to t. If this is right, output this. That's going to be student problem. So let's actually understand what t will this algorithm work. We'll set L to set that minimize t as small as possible. Is the algorithm clear? So we have two sort of requirements. What's the requirement we want? So there are the requirements. One is can find a non-zero solution by interpolation for any input data set. And two, every polynomial p that has agreement t should appear as a factor. That's what we do. We don't want to miss out any of the factors. So these are the requirements we want. Every P that has agreement at least P with the data must appear as a factor y minus p of x of q of x. We want this. So these are the requirements which we have. So let's now let's find out the setting. What is the interrelationship between n, k, l, and t, such that both these requirements can be met. So let's go to the first one, which is the interpolation requirement. This is what we had said already. So a non-zero solution exists if number of variables is greater than number of equations. Number of variables is exactly number of monomials x bar I, y bar j, such that I is less than or equal to L and j is less than or equal to n by L. That's exactly L plus 1, n by L plus 1. And this has been set up such that this is a number larger than n always. Since L plus 1 is greater than n for all L non-zero solutions. Number of equations. Okay. So that's the first requirement. First requirement is L has been already chosen. This L and n by L has been chosen for that. The first one. The second one is we want now if a P agrees with the data on a large number of points, we want this P to actually be this P should appear as y minus P of x should be a factor of Q of xy. Equivalently, so let's say so we want the following thing. So if some condition on L is satisfied, then the following should be true. If P of x satisfies, then the following is true. P of x satisfies number of I in n such that P alpha I equals beta I is greater than or equal to P, then you must have Q of x comma P of x should be identicals. We want this to happen. If this is if this happens, y minus P of x will be a factor of Q of x. So we want this to happen. That is, if P of x happens. So let's find out what's the. So just let's define the polynomial R of x, which is Q of x comma P of x. So P is some polynomial that has significant agreement with the data. No, we haven't yet. If L satisfies some parameter, we have to figure that out. We'll figure it out by the end of the proof. If L satisfies some parameters, then every polynomial P that has significant agreement with P should satisfy the fact that Q of x comma P of x. That's what we want. So now what is L? This is a condition that we will. Right now it's This is the condition that we're going to fill soon. Yeah. Let's stare at this. What's the degree? So what's the degree of? So what's the degree of R as a polynomial?
R plus L plus N divided.
By the way, we need to show that this one, this is R of X is identically 0. The only way we know how to show it is the number of solutions for this is more than its degree. Then it has more roots than its degree. Therefore, it has to be identically 0. That's the only way we know. Notice we already know that it has a large number of roots. So every point of agreement, every alpha I, beta I, which is in that set, is the solution for this. So is one in which R of alpha I. So every alpha, so what we have is the following. If P of alpha I equals beta I, this is the point of agreement. That is the point of agreement. Notice Q was chosen, Q has already been chosen so that Q of alpha I comma beta I is 0 for all the data points. Now, if P of alpha, that means that we do have then R of alpha I is 0. R of alpha is 0. That in other words, X minus alpha I is a factor of R of X. This is true for every single point of agreement. So if you show that the degree of R is smaller than T, this will force that R has to be identically 0. So now let us stare what is the degree of R. Hence, what I'm saying, the product of X minus alpha I, such that for all I such that P alpha I equals beta I, is a factor of R of X. That's fine. But now let's stare at degree of R of X. Degree of R, there's only one degree. What is it? What's the bound that we can put on it? So it's X degree, from X it gets L. Now because you're plugging in P, that can go as large as K minus 1 times N by N. So if L greater than, if P greater than L plus K minus 1 by N by L, then R must be identically 0. Is that fine? If I have chosen P to be, if L satisfies that, this is, we will eventually set L such that T is as small as possible. So the thing for the condition over here is exactly if T is larger than L plus K minus 1 L by N. N by N. Sorry. N. Is that clear? Now this is true. So as long as P and T, N, K, and L satisfy this, so this is the only requirement we want. If P, N, K, and L satisfy this, then we get that. We will want to set L so that T is as small as possible. T has to be this one. So what's the smallest? You want to choose it so that this is this one. The smallest setting of now this number is always at least the geometric mean of these two. And there is a setting for L which does this. So just set L to be equal to square root Nk minus 1. That will set this one, and then at that point of time, and so T is greater than, in that case, is greater than 2 square root Nk minus 1. technically we should all be like ceilings and stuff. I'm going to sort of work it here. I'm going to work it. We can be careful that all of these actually work. Because L has to be a parameter. So actually L you can set it to be this because that's just a bound on the degrees. You can set L to be this and P will be in. So these are all bounds. So these are, I'm not stating the degree is exactly this. You can do this. So what I'm claiming at the end of this, stating that theorem can decode if number of agreements is greater than 2 square root n k minus. That's the theorem number 2. And I mean less decode, I mean efficiently. Is this fine? Questions on the problem so far?
So at the beginning of lecture, you said that Sudan, you claimed that the Sudan algorithm, the 2 is inside the square. So is it improvement?
Yeah. So the first, to them first attempt.
Okay. So we have second method here.
They will have the second attempt of them. I will look at, we'll stare at the algorithm and see there's some minor modification you can do to actually put the 2 inside the square root, and then we will need a serious modification to remove the 2 completely. Yeah, so that's why this is Sudan's first attempt, it's not the second attempt. Yeah. But if the algorithms are for clear. So what can we do to improve this? So by the way, it's magical that this works. This was just an attempt to stare at the Welsh-Berle algorithm that only gave you unique decoding because degree of y is 1. So we just sort of gambled and said, what happens if we allow the polynomial to have larger degrees? Will we get something better? Notice this is not always better. Right? This number, if it was a Johnson bound, you know that square root nk is always greater than n plus k by 2. The geometric mean is always. It's not clear that this number is better than n plus k by 2. There will be settings for which this is actually worse than n plus k by 2. It just says that there is a certain setting of n and k for which this one will be smaller than the. So if the geometric mean and the arithmetic mean are significantly apart, then even twice the geometric mean is going to be smaller than the arithmetic mean. It's not all, when n and k are very, very close to each other, this is not going to happen. It's only when n and k are significantly apart from each other, this is going to happen. So for those settings, this algorithm does better. For the other settings, you go back to the Welsh-Berle algorithm. This T is actually worse than what Welsh-Berle is going for. Yeah, so this was just a gamble. We just paired Welsh-Berle algorithm, asked if we increase the degree, can we do something? And it shows, yeah, you can do something if for certain settings of parameters. So if you can get 2 to the power of n k minus 1, there might be a choice of n and k for which this is better than n plus k by 2. But now let's stare at this algorithm a little more and see, are we doing something weak? Are there some improvements that can be done? Notice that what we really get, so there are only 2 requirements. The interpolation requirements, the number of variables will be larger than the number of equations. And then you wanted this thing to satisfy the q of xy. For every point polynomial which has significant agreement, it must satisfy that q of x comma p of x is identically 0. These are the 2 requirements which we had. Let's see if we are doing something. So that's the first one. Notice that to do the second one, so the first one, the second one where was more was involved. The degree of what we were comparing p to the degree of r. That is, every point of agreement contributed a root for r of x. And we wanted to compare the degree of r to this t. And there we have this L plus k minus 1 n by L. Now when you do this, it seems as if this comes because of the degree in x. This comes because the degree in y, and each degree in y has to get multiplied by k minus 1 because you're potentially plugging in a polynomial p of x which is degree as large as k minus 1. So then you should not be actually looking at an x degree, y degree. What you should be doing is in which the x and y degree are sort of balanced. That is, you look at polynomials such that with weighted degree, that is, every degree in y is you charge it k minus 1 times the degree in x, so that because a degree in x is only contributes L, whereas the degree in y contributes k minus 1 time. So we'll define this new notion called the weighted degree. So to balance of, to balance the imbalance in the x and y degrees. We'll define this notion. We'll define something they call an AB weighted degree of a polynomial. So what was the degree so far of a polynomial? We talked about the x degree, the y degree. The AB weighted degree of a monomial x power I, y power j is going to be a times I plus b times j. That is, x gets weighted a times, y gets weighted b times. And what we really care for is 1 k minus 1 weighted degree of q. We want to look at the 1 k minus 1 weighted degree. That's the degree that in q of x comma p of x, if you want to look at that degree. So this, so let d be So let d be, let's define d to be the 1 k minus 1 weighted degree of q. So the same argument at the plane, if t is larger than d, then q of x comma p of x is identically 0 for every p with significant agreement. Exactly with agreement at least. So instead of asking that the x degree be L and the y degree be n by L, we will ask that the 1 by k minus 1 degree. So we will modify the algorithm. Now not have the parameter. Only going to have parameter d. So find a non-zero polynomial. So what we're going to change this to the following. So that the 1 k minus 1 weighted degree q is less than or equal to d, and q of alpha I beta I equals 0 for all I in n. And the second one will be as optimization. Okay, so we have this, and the second step is going to be exactly the same. And the reason for doing the first step is this is what mattered was not, it didn't matter to look at x degree separately, y degree separately. All that we cared about the x degrees and y degrees was just to ensure that the degree of R of x, which is defined as Q of x, P of x, was smaller than the number of ugly loops. So then you chose that D to be larger than D. So now we have to find out now step 2 the analysis becomes extremely simple. Step 2 the analysis is before it just says if D is larger than T, then every P will become a root of every P that has agreement at least T will be a root of Q of x comma y. Step 1, we need to choose D such that the number of monomials of that type is more than the number of equations. So step 2 is the interpolation requirement. So let's now see. Step 2 requirements are just have now become easy. That's just D greater than T. That's just the step 2. Step 1 requirements. Step 1 was the interpolation. So now we need to look at the new number of variables, the new number of equations. Always the number of equations has been n. What's the number of variables? Number of variables is the number of pairs I and j such that 0 less than or equal to I comma j is less I comma these are integer, and I plus k minus 1 j is less than or equal to. This is what we are looking at, the size of this. So let's actually count. This is exactly the number of variables. Let's actually count this set. So notice J can take values from where to where.
This summation to T by K minus 1.
Yeah, so J can take a value only up to L going up to T to K minus 1. That's exactly what you said. So J can go from 0 to L. And once the J is chosen, I can go from where? 0 to D minus K minus 1 J. And for each of them, you have 1. So that's exactly this guy. So let's open this up. So this is summation J equals 0 to L. What is this? This is D plus 1 minus K minus 1 J. What is this? This is D plus 1 into L plus 1 minus K minus 1 summation J equals 0 to L J. Which is what? Which is D plus 1 L plus 1 minus K minus 1. This is L into L plus 1 by 2. Right? Some common factor out. So this is, let's take L plus 1 by 2. 2D plus 2 minus K minus 1 times L. Notice I want a lower bound on this. What we want is a lower. We just want to make sure that this number is larger than n. We want to choose D such that this number is larger than n. Now, I want to say that this quantity is greater than L plus 1 by 2 into D plus 2. Why is this? Since L is less than or equal to D by K minus 1. Yeah. Sorry, L is greater than or equal to. Yeah, what do I mean? I need L is less than or equal to this, therefore this is greater than or equal to this. Yeah, L has been chosen to be the floor of that. Therefore, L is certainly smaller than this. So when I subtract K minus 1 L, I'm subtracting at most D. I get D plus 2. All of this is just to make this form nicer. So then I want to say that this quantity is now at least D. I want to remove that. I want to just keep D in mind. This one I want to say this is at least D into D plus 2 by 2K minus 1. Since here I'm going to use the fact that L is greater than or equal to D, K minus 1 minus 1. This is well, I got this. So as long as I choose D such that this number is greater than N, then the interpolation conditions are met. If we choose D such that D by 2 by 2K minus 1 is greater than N, then interpolation condition. That's the here. Notice D is the floating parameter. We need to get rid of D. So what is the D will do? So just set. So let's set D to be equal to. So notice we want to set D such that what do we want of D? We want D to satisfy this. D should also be larger than P. And we want T to be as small as possible. So we want the smallest D that is going to satisfy this one. Notice this is approximately like D square by 2K minus 1 is equal to N. But ignore the D plus 2 factor. Therefore, basically we want D to be square root of 2K minus 1. That's exactly what we have to be. We'll set D to be the floor of the ceiling of 2K minus 1 the square root of this. And notice this is T. D were equal to D, and also T to be the same number. T to be equal to therefore, for this one, what we have is that we now have Sudan's theorem, main theorem. Can efficiently just equal. In Solomon 4 with agreement, with number of agreements greater than 350 for every 2 that is rho is greater than 1 minus 2. Yeah, that should all this improvement was to push the 2 inside. Yeah, because we were looking at the x degree and the y degree separately, it didn't make sense to do it. You just look at it together. That's all that mattered for the analysis. We do it that way. All of this there is there in the paper from 1996. So far, so good. Notice, by the way, so this does tell you that so you can come up with. So we are basically saying that we can sufficiently list decode up to this point. But once again, this point need not be smaller than n plus k by 2. There are certain settings for k and n, in particular when k is very much smaller than n. When the rate is really, really tiny, then this is actually better than n plus k by 2. In those cases, we are stating we can efficiently list decode much beyond the unique decoding. So what this is, and the question still remained open if you can do better than this. That is, can you improve this into all the way to the Johnson values? The question so far is this clear, and then we will see in the next 15 to 20 minutes, we will see Guruswami-Sudan further improvements to push this all the way to the Johnson value, to completely shave off the factor. What have we done so far? What were the two steps? The first step was given algebraic explanation for the data. What was that mean? Just found a non-zero polynomial Q that passes through each data point. That is, want to find a Q with some degree restriction, so that Q of alpha I, beta I is 0. That's the first step. The second step was show that if any point, any polynomial P that has significant agreement will then have to be, if that polynomial, if any polynomial P that has significant agreement, then the corresponding factor y minus P of x will be a factor of the polynomial Q of x comma y. So there's two steps here. The first was solving a linear system. The second was actually fitting. Now you could ask a question, what was Guruswami-Sudan? Once again, we'll state this, we will see that there's no reason to believe this will work. We'll run the parameters and we'll show that it works. Just like over here, it was unclear why this was this one. It was a promising step, moving from degree y in 1 and y to larger degree allows at least you can have the problem. And we are able to show that once you do this, there are certain settings for parameters k and n where this actually beats the Welch-Perleka algorithm. And what we'll do is, the first step was we said that it explains the data. What does it mean explains the data? The polynomial Q of xy passes to the point alpha I, beta I for every I. And we said it just passes once. You can say what happens if it passes with multiplicity? That is, it hits the point alpha I, beta I, not just once, but several times over. So improvement. So basically, the idea is the following. Idea is incorporate. I have to even define what this means. Incorporate multiplicities. Is it both in step 1 and step 2? Step 1 will mean that every data point Q of xy does not pass through the data point just once, but say some r times, whatever this means. You say it has a multiplicity. That will tell you so that this will give you some interpolation conditions and you'll factor. The second step says that for every point of agreement, we will get that a point of agreement is not just one point of agreement, it actually gives you r point of agreement. Therefore, B will actually get compared to, if B was the weighted degree of Q, 1k minus 1 weighted degree, every point of agreement will not just give one root for Q of x, for R of x, it will give you R roots for this one. Therefore, as long as B is greater than PR, we will still be able to do something. So they will be, so they basically, I'll say informally what this means. That is basically for step 1, this is adding more restrictions. That is Q of xy has R roots. I have to define what this even means. For univariate fact, this one is clear. When I'm taking it R root, it means x if a point passes through a particular thing r times, it means all the lower order r derivatives vanish. For multivariate things, it's unclear. We'll make this formal as r roots at the data point alpha beta. Right? And step 2, every point of agreement gives r roots of r of x, which has been defined to be u of x, p of x. There's two things going on here. So notice the first one, by adding more restriction, the number of variables in, if you working with 1k minus 1 weighted degree polynomials d, the number of variables that's fixed. That's exactly the number of monomials of this type. That's the number d into d plus 2 by 2k minus 1, which we saw before. Now you are just adding more restrictions. You're adding more equations. That is the number of equations you are increasing. This means that d will have to only increase further. Notice that the effect of this means number of equations are increasing. That implies d must be larger. Because D directly determines the number of variables. This seems to go in the wrong direction because D is going larger. We want D to be smaller. But the other hand, what's happening over here is every point of agreement. Here, what happened is the number of roots. Every point of agreement previously contributed to just one root for R of X. It's going to contribute. It's going to contribute R roots. Therefore, here what we need is. This will require D to be just larger than P by R. We have to make things precise. So what you want is not just, this is the degree of the polynomial. Sorry, this is not, sorry, so if T is larger than, if R times T is larger than D, then you would get, then the polynomial R will vanish. So this makes T small. The requirement for T was to be as large as P before. Now it is smaller than P by this one. And there's a tension between these two. And it so happens this tension works in our favor. We'll have to actually check it out. It will be nice to give a reason why this tension works in our favor. And I think to this day, we don't understand why the Guruswami-Sudan actually, this way of doing it, actually, why it actually gives it. We'll see the parameters, it works out. And I've asked both Madhu and Venkat to do, sir. I don't think they have an explanation today. If you look at the book, they'll give you pictures as why this is this one, but all those pictures are just intuition why it might be this one. There's no clear reason why this adding multiplicities helps. But it has been extremely powerful. In fact, this whole notion of multiplicities led to these Kakea sets and all of the, if you were there last week for Barack versus talk, he used all of this machinery that was used, basically came out of the work of Guruswami-Sudan and subsequent work due to Veer and all. They built these better Kakea sets, which then led to better coverings of the lattice and so on later on. So it's quite remarkable that this works. I don't have a formal explanation why it works, but it does work. But let's, well, now I want to formulate. So yeah, so that's exactly what I'm going to define. So we'll say that the definition. So Q of xy has R roots. So the point is, I don't want to define derivative. I want to be keep away from derivatives because derivatives are we could define it in terms of derivatives. Say all the rth order derivatives are zero, or finite field derivatives are a thing because x power p is a non-zero polynomial, but its derivative is p into x power p minus 1 because the characteristic is just is a zero polynomial. You don't want to do such things. So you have to actually work with a notion called assay derivatives, not derivatives. This one?
Okay, the derivative of is
No, but the derivative of, so the derivative of x power p is 0, but you will see that that derivative, the notion of derivative is not what I don't want to keep this as a derivation of derivative. If you actually be clear, it has a derivative. So I'm going to avoid the whole thing by defining have R roots in, without breathing the word derivatives. I'll define it just for it's easy for it. But the equivalently, you can define everything that I've said is formally can be done in terms of what is called Hasse derivatives, which is what you should be working with if you're working with finite roots. Let's say Q of xy has R roots, but let's say at the point 0. This what does it mean Q of xy? This just means if you look at it as a polynomial, it has no what does it mean? It has one root at 0, 0. That means it has the constant term is not. What does it mean? It has two roots at 0, 0. It doesn't have any linear term also. So R roots means A. When you look at the polynomial expansion of Q of xy, that it has no term in which the degree of there's no x bar I, y bar j term in it, so that I plus j is less than or equal is less than R. Okay. So R root is the coefficients of x power I, y power j for any ij satisfying I plus j is less than R is 0. That's going to be my definition of. So this is at the point 0, 0. Now to define it at some other point alpha beta, we will just translate the curve Q of xy, we'll move it to Q of x plus alpha, y plus beta, and say that new guy should basically what I'm doing is I'm doing Taylor instead of expanding it around 0, 0, I'm expanding it around alpha beta, and I'm saying around that you should never have this. So, and this is just for this. This is at the point 1. So one definitely Q of x y has R roots and alpha beta if Q alpha beta of xy, which is being defined to be this polynomial, we can define it to be Q of x plus alpha, y plus beta has R roots at zeros. Okay. So that's going to be my definition of the fact that a multivariate polynomial has R roots at a particular point. So what we'll do is we'll just translate the point to the origin and then say that if you look at it has no term, no all the coefficients of all the monomials of degree less than R are all 0. That's what. Order R square. In fact, for bivariate, it's exactly R plus 1 choose. And that number will be important. But let's exactly see that now. So let's just now say now I'm going to write the Guruswami-Sudan algorithm. There will be two parameters now. There will be D and there will be an R, which is the multiplicity parameters. We will fix both of them later. And this will be that the first term will be as before, the 1k minus 1 weighted degree of Q is less than or equal to D. And the second term will be Q of xy has R roots at alpha I beta I for all I in n. So that's going to be the modification. That's Guruswami-Sudan modification. And then we'll do the same thing as well. So let's
Here, instead of factors should be art of the. Here only y minus p is whole power r.
no, we'll see that it will just be y minus b of x is a factor. So let's see both the as before. Let's look at step 1 requirements. Once again, number of variables is the number of monomials, and that we saw is d into d plus 2 by 2k minus 1. That didn't change. What's the number of equations? Firstly, is this a linear system? Firstly, is this a linear system? Q of xy has R roots at alpha I beta I. Notice this is a linear system. That is basically, I'm just getting Q of x. So look at Q of x plus alpha. So what does it mean to say Q of? Let's look at alpha beta, and I want to say in this word, let's see, what does it mean it has one root at alpha beta? Of course, it's stating a Q of alpha comma beta is 0. That's equivalently stating Q of x plus alpha, Q of y plus beta. Expand it out and look at the constant term. That constant term is 0. That constant term, notice it's a linear combination of the coefficients of Q. It might involve polynomial high degree terms in alpha and beta, but still it's linear in the coefficient. Therefore, has one root is clear, one root is just plug it in. Now, if you want to say that it has two roots, you just take Q of x plus alpha, y plus beta, write it down as a polynomial, and say that for every such monomial of the term x bar I, y bar j, it's that monomial is 0. Now, the monomial will all be linear combinations in the coefficients of Q. So they will all be a linear system. It won't be linear in alpha and beta, but I don't care. That I can afford to do. It's linear in the coefficients. And how many such equations do you have? You have as many as this is exactly where for every monomial of the type x bar I, y bar j, so that I plus j is less than r, you are going to have a equation. How many such are there? There are r into r plus 1 by 2. Therefore, this is basically n times, this is n times number of ij such that 0 less than I j and I plus j is less than r. This is n times r into r plus 1 r plus 1 choose. Okay. So here the equations turn out to be, here what we need to have d into d plus 2 by 2k minus 1 should be greater than n into r plus 1 by 2. So we will set d to be equal to ceiling of k minus 1 n r into r minus 1. So is this r plus 1 choose to, or just r choose to? What is it? I plus j less than r. So I can take any number between
I plus j plus k equals 2r.
I plus j plus k equals
Percent.
r plus 1 2. Okay, fair enough. So the number will 3. Huh?
Square root.
Yeah, this is correct. If I choose d to be this quantity, this will satisfy the problem.
That is r after.
I think the plus 2 is what will give you this one. So you choose this d and put it into the d plus 2. It happens to work. So I don't want, I want to skip this calculation. If you choose this, then that condition is satisfied. So this is going to be our to satisfy interpolation. Minus. I want to do the parameter. I want to do the following name or lemma. I want to, we will do this name shortly, but if I want to say if D is smaller than dr, then and P has T agreements greater than or equal to T agreements, with the data, then R of x defined to be Q of x, P of x is identical. This is a claim which we have to prove, but let's defer this proof for a few minutes. Let's first see why this will complete one. So I want to now choose. So I want to choose T to be greater than D by R. That's how small I can make T to be. D itself I have set it to be square root k minus 1 n r minus 1. The meaning of this. So in particular T, I can set it to be square root k minus 1 n 1 minus 1 by r. Okay. I haven't yet said what r I'm going to choose. So I will choose r to be equal to set r to be equal to 2k minus 1 n. Then T, that will imply T is greater than square root k minus 1 n minus a half. Therefore, this is just greater than square root k minus 1. Yeah, so that's the final setting parameters. So, well, still haven't yet proved the claim, but the final theorem of Guruswami-Sudan is the following theorem. Guruswami-Sudan. And let's decode its following codes. If number of greater than or equal to whatever the row is greater than or equal to 1 minus r, which is exactly I finished with name and wrap up. I'm already able to wait. So The claim, what's the claim saying? The requirement on B, previously was B was less than T. Now it has become B is less than TR. The requirement on B has considerably reduced. And why is that? We want to say that the following proof of claim is this. If P of alpha equals beta, let's take a data point, in this case an agreement, that is an agreement point. Then, so suppose we show the following. Suppose we do the following. Suppose we show for every point of agreement that is P of alpha equals beta. We have previously what did we have? We had x minus alpha was a factor of r of x. We have now x minus alpha to the power r is a factor of r of x, which is defined to be q of x comma p of x. Suppose we show this following thing. Then we are done, because each point of agreement contributes a factor of the form x minus alpha per r. If there are t points of agreement, each of them will contribute x minus alpha I to the power r. There will be tr of them. The degree of r has to be at least tr. If r has a smaller degree than that, then it has to be the zero polynomial. So this is what we show. We now prove the integrate back. So we prove this. So what we need to show is we need to show that alpha beta that is x power r is a root of x minus alpha power r is the root of q of x comma p of x. Let's look at the special case when alpha beta is 0. Sorry, alpha beta is 0 comma 0. It is I moved the origin. You can do this translation and all. What do we have then? We then have that r of x, which is q of x comma p of x. What is this? What's the, let's stare at this. What do we, so r of x is, what's the constant term in p of x? 0, because the point is alpha beta. So the special case, let's do that first. Since p of alpha equals beta, constant term of p of x is 0. Now let's look at r of x, which is q of x comma p of x. And let's ask what's the factor of x power r that defines this? We know that when we expand this as an x and y polynomial, it has nothing of the form x power I, y power j, where all the terms are less than r. But now this always looks like this is some polynomial in the form q of x, some ax plus some higher degree terms. So the least degree term in R is at least R by a choice of. Is that okay? Yeah. So that is just a choice. And this is for alpha beta being 0, 0. For every other alpha beta, you just suitably translate and do it, everything works. It's just an ugly translation you have to do, but the exact same proof. Well, that's exactly. So in other words, every point of agreement contributes not just one root. So that is x power r is a factor of R of X in this case. The general alpha beta X minus alpha power R will be a factor of X. The proof is simple. That is actually the Guruswami's entire Guruswami-Sudan algorithm. It's quite remarkable. It goes all the way up to the Johnson radius. Okay. So what next? I'll just say there are several things which are going to happen in the next lecture as well as in the problem set. So what have we done so far? We have done list decoding of the Solomon codes. We have shown that it's list decodable all the way up to the Johnson radius. Now you can ask what, okay, that's great. So I have a code over a large alphabet which is list decodable all the way up to Johnson radius. Can I get a code over the binary alphabet, which is what we really care about, which is also list decodable? One. But we'll show that for that. And what's one way of doing it? Standard way we did it was you concatenate. You concatenate with some nice code. So you binary in the binary case and the small code, you know it's list decodable just because you can brute force this decode. The small alphabet, if by Johnson radius, you know it's list decodable. You just brute force list decode it. You can go over all code words because the entire code is over a small space. It's a number of code words only polynomial. If you brute force this code, concatenate. Concatenate and hope you can get a list decodable code at the end of it. You'll realize that if you run the natural algorithm, you list decode the inner code. You get a number of locations for each guy. Now you have to list decode the outer code. But the outer code, the input is not you for every location, you're not getting a value, you're actually getting a list of values. This is not the list decoding problem. List decoding problem was for every the outer code for every at every location, for every alpha I, you got a beta I. But now instead you've got a list. And you want to find polynomials that agree with some element in the list. So we need a stronger problem than list decoding, which is called the list recovery problem, not the list decoding problem, in which instead of a beta I, you are actually given a set. You're given a set at every location, and you want to find a polynomial that for most values of alpha I has an element in the set that it passes to. This is called the list recovery problem. You can formally define it. So what we'll show, the problem set has two problems which basically deal with list recovery. It formally defines list recovery. It shows that if the inner code is list decodable and the outer code is list recoverable, then the concatenated code is list decodable. And then you can also show that if the inner code is list recoverable, the outer code is list recoverable. When you put them together, you will get a list recoverable code. So list recoverable is such an object that when you compose it with itself, will retain the property. Therefore, to get over the binary code, we need a list decodable inner code and a list recoverable outer code. And then you realize that the Guruswami-Sudan algorithm actually is not just list decodable, it's actually list recoverable. So there's yet another problem in the problem set, which will show that if you stare at this algorithm long enough, what you actually get is a list recoverable algorithm, not a list decodable, not just a list decodable algorithm. So you have an outer code, which is not just list decodable, but actually list recoverable. Concatenate it with a binary code, which is list decodable, and you will get codes over the binary alphabet, which are list decodable up to this one. There are 3 problems out of the 6 problems in the problem set. 3 problems will discuss this. This whole discussion is spread across 3 different problems. Each of them will solve one part of this puzzle. So it's a good idea, even if you're not doing the problem set, you're not submitting it for actually do the problem, look at the stare of the problem, because they solve each part of this puzzle. And if you put them all together, you will get list decodable codes over the binary alphabet. Of course, these don't go up to the Johnson radius. There's a when they don't go up to the Johnson radius for the binary alphabet, because concatenation is going to cause a deterioration in rate and distance. They do give you some list decodable codes. At the end of this, you will get some list decodable. What? It will be well beyond the unique decoding radius. So, for instance, you will get binary code which are list decodable even with errors. So a binary code can have distance half. at most half, we know this. So you will be able to get binary code which are list decodable even if the number of errors is half minus epsilon. That's almost everything has been all the way up to distance you're corrupted. Previously, we could never do a recovery beyond 1/4. The binary code can have distance best at half. Therefore, even no matter what its distance, you can't do better than 1/4. This is going to say you can recover even if the number of errors is half minus epsilon. So the end product of these three problems in your problem set will give you binary code which are list decodable even when there are half minus epsilon errors. Which is quite something astounding. That is, the distance of the code is close to half. And I'm going to say I'm going to erase half minus epsilon, not erase. I'm going to make half minus epsilon of them. I'm going to flip it off. And yet you will be able to list decode. Give me a short list. In fact, just a polynomial size list and say the code word has to be one among this. And yeah, so it will just come. We got by concatenating the Reed-Solomon code with a binary code. Brute force list decoding algorithm to binary code. And all of this will be split across three problem sets. 3 problems in the problem set. So I would strongly recommend you do the problem set. Next, what's the next topic we're going to go? So far we have talked about codes which are decodable up to the Johnson radius. You can now look at this for each of our codes which we have seen so far and ask them if they are list decodable. What we'll ask is, are there codes beyond which are list decodable beyond the Johnson radius, all the way up to list decoding capacity? We show that there are non-explicit constructions we have shown. What we'll now show is we will come up with a new code which actually goes, which is efficiently list decodable all the way up to list decoding capacity, all the way up to 1 minus r. So far it's 1 minus square root r is the Johnson radius. We'll go all the way up to 1 minus r. So that we'll do. And we will also, so the next 2 topics for list decoding will be to come up with an explicit code, which is list decodable all the way up to capacity. And in fact, if there are two are this one, we know only few such codes, and both the codes are codes which you have seen in the problem set. It's the folded Reed-Solomon code and the multiplicity code. These codes will be the ones. Then we'll see an efficient list decodable algorithm for the binary code. For the Hadamard code, this one, it's unclear why I am calling efficient with this one, but we'll make all of this precise. So these will be the topic for the next 2 lectures in the series.
The list decoding capacity is 1 minus
Yeah.
The book says is actually H inverse of 1 minus.
Yeah. So if Q is for a fixed Q, it's 1 minus H inverse of 1 minus R. If Q is going to infinity, the H inverse of 1 minus R is actually 1 minus R. I'm looking at large fields. I'm looking at large alphabet. If you're going to fix a particular alphabet, then you have to look at H inverse. If you're going a large alphabet, so initially we will do first over the large alphabet. So we'll get 1 minus R. Then we'll do concatenation to get it to. Yeah. Okay. Long lecture.